Hello dear students, welcome back to the lecture series on major theory with the course statistics. Course statistics is real analysis is the second with course code MMTC 202. Today in this lecture we are going to discuss almost everywhere property and measurable functions. So first we define almost everywhere property. Almost everywhere property, which is abbreviated as A dot E. Almost everywhere property. Now suppose we have a given major space X as mu, given a major space X as mu, where this X is a non-empty set, S is a sum bearing on X, and mu is a measure on X. And let mu star be an outer measure. An outer measure generated by mu. Okay. Then a relation. It's actually a relation on elements of X involving the elements of X is said to hold almost everywhere. Is said to hold almost everywhere. Is said to hold almost everywhere if the set of points A, which is subset of X, if the set of points A for which the relation fails to hold, is a null set. It's a null set, that is, its outer measure is equal to 0. So that's a definition of almost everywhere relation. Given a major space X as mu, and this mu star be an outer measure generated by the measure mu, then a relation which involving the elements of X is said to hold almost everywhere if the set of points A, which is the subset of X, for which this relation fails to hold, have outer measure 0 or is a null set. So let's take some examples on this almost everywhere relation or almost everywhere property. Now let's take this major space, the vague major space in which the set is the real line, and this major space it's a class of semi-closed intervals, and that's a vague measure on that class of semi-closed intervals. Now let's define two functions f g from R to R, defined by f of x equal to 1 for x whenever x is an irrational number. X is an irrational number, and its value is suppose its value is say x square. If x is a rational number, so take this function fx, which is 1 on irrationals and x square on rationals, and take another function g, which is defined by it's equal to 1 if x is an irrational number, and it is suppose equal to x cube if x is a rational number, if x belongs to q. Then we know that this Lebesgue measure of q is 0. Lebesgue measure of q is 0. So we can this q is a null set, as already discussed. Set of rational, it's a countable set, and therefore it's a null set. In this measure space, so it's a null set with respect to the Lebesgue measure. And you can see that the outside of this set q having Lebesgue measure 0, fx and gx, they are equal actually. So then we can say this fx is equal to gx for all x in q complement. For all x, while x is an irrational number, and they are not equal on rationals, and they are equal on irrationals. But we know that this the Lebesgue measure of q is 0. It's a null set. So the equality property does not fails to hold on the set A, which is a null set actually, because this equality fails to hold on q, and q is a null set, and outside of this set q equality hold. So therefore we can say this f is equal to g almost everywhere. You can see f is equal to g almost everywhere, because this equality does not hold on q only, and we know that the Lebesgue measure of q is 0. Therefore q is a null set. So equality does not hold on a null set only. So that's why this equality, it holds almost everywhere. That's an example of almost everywhere relation. So let's take some more example which we are going to use in this section. Throughout this section, x s mu is a measure space. It's a fixed measure space. So throughout this section, x s mu is a fixed measure space. Throughout this section, x s mu is a fixed measure space. So let's define some almost everywhere relations. Let's define a real valued function is let f comma g be two real valued functions on x. Their function is from x to r, while x is a measure space, x s mu is a measure space. So these are two functions. They are real valued functions on x. Then the first one, we say this f is equal to g almost everywhere if the outer measure of a set which is subset of x such that fx not equal to gx is equal to 0. Means the set where this property fails to hold is a null set. Where this equality does not hold is a null set. Its measure is 0. So this means f is equal to g almost everywhere. And second one, we say f is greater or equal to g almost everywhere if this property fails to hold on a set, on a null set. That's if outer measure of a set which is subset of x such that this property fails to hold. Means fx is less than gx. Fx less than gx is a null set. Its outer measure is equal to 0. And third one, suppose we have a given sequence. Fn is a sequence of functions from x to r. Fn is a sequence of functions from x to r. Then we say this Fn, this sequence Fn, it converges to f almost everywhere. It converges to f almost everywhere if if the measure of the set of points where this convergence does not hold, f(x) does not converge to fx is equal to 0. Where the set where this convergence fails to hold is a null set. Its outer measure is 0. Then we say fn converges to f almost everywhere. And fourth, we define fn. We say fn increases to f almost everywhere. So increases to means this is an increasing sequence, but here it's almost everywhere. Therefore, this sequence is increasing, but almost everywhere. And convergence is also almost everywhere. So it means that if we say fn increases to f almost everywhere, if fn less or equal to fn plus 1 almost everywhere. It is this sequence is an increasing sequence almost everywhere, and this less or equal to are already defined here. As we define it here, greater or equal to, in a similar way we can define less or equal to. F less or equal to g almost everywhere if the measure of the set, outer measure of the set x belongs to x, such that fx greater than gx is a null set. So that's a definition of f less or equal to g almost. Here we can that this fn less or equal to fn plus 1 almost everywhere means the set where this property fails to hold, means where fn is greater than fn plus 1 is a null set. Okay, so first if this hold and fn converges to f almost everywhere, that's already defined here, converges almost everywhere. So the null set here and null set here they may be different. And fifth one, we say fn, the sequence fn, it decreases to f. It decreases to f means that this is a decreasing sequence almost everywhere, and the limit of this sequence is f almost everywhere. Almost everywhere. If fn less or greater or equal to fn plus 1 almost everywhere, and limit of fn is f almost everywhere. So these are some fundamental notations which we are going to use in this chapter, in this section. Okay. So next we define measurable function, then we give the characterization of, then we state a theorem, then we prove a theorem which gives us the characterization of a function, characterization of measurable functions. Okay. So first we define measurable function. Definition of measurable function. Okay, so access means a fixed measure space that I have already discussed here. So let f be a real valued function. So first it should be noted that this measurable function is a real valued function here on a measure space x. Be a function, be a function, be a function. As in case we know that the definition of continuous function between the topological space, a function is continuous between the topological space x and y if the inverse image of an open set is again an open set. So here the definition of measurable function, on this side we have open set because R is a real line with the usual topology. It's a topological space. So on this side we have open sets, but on this side we have measurable sets because X is a measure space. So we say the function f is measurable if the inverse image of an open set is measurable, because inverse image of any set is subset of X. But if we choose here particular sets, particular subsets which are open sets, if we want to calculate the inverse image of those open sets, for the function to be measurable, the inverse image of those open sets must be measurable subsets of X. So then we say such a function is measurable. Okay, it's if F inverse of O, when O is an open subset of R, is measurable set is, because F inverse of O is a subset of X, is measurable set for every open subset O of R, for every subset O. If inverse image of an open set is measurable for every open subset O of R, then F is called measurable. Then F is called a measurable function. Measurable. Then F is called a measurable function. That's the definition of measurable function. So next we give its characterization in terms of open intervals, because we know that every open set of real line R can be written as a countable disjoint union of open intervals. So there must be some sort of characterization in terms of open intervals. Okay, so let's state that theorem here. So what's this theorem? For a function f, function f from x to r. For a function f from x to r, the following statements are equivalent. The following statements are equivalent. The following statements are equivalent. So what are the statements? There are 6 statements here. There are 6 statements. So first statement is F is measurable, means inverse image of open set is measurable. F is measurable. And second statement is F inverse of any bounded open interval. AB is a bounded open interval. Is measurable. Is measurable for each bounded open interval AB of R. For each bounded open interval AB of the real line R. Okay. F is measurable, means inverse image of every open set is measurable. Its equivalent to inverse image of every bounded open interval is measurable. And third statement is it's equivalent to F inverse of C. F inverse of C is measurable. Is measurable for each closed subset. For each closed subset C of R. And fourth statement is F inverse of this unbounded interval. It's A to infinity. Inverse image of this interval is measurable. For each element A of real line R. And fifth one, it's closer on that side, F inverse of minus infinity to A is measurable for all A belongs to R. And the sixth one, that's last statement, F inverse of B is measurable, is measurable for each Borel subset, for each Borel subset B of R. You know that Borel subsets, eh? The Borel subset, the sigma algebra generated by open subsets of R, and the members of that sigma algebra are called Borel subsets of R. So that's the statement of this theorem. There are 6 statements, and we need to show that these 6 statements, they are actually equivalent. They are actually one. Okay, they are not different actually. And in future, we are going to use these 2 statements for measurability because they are equivalent to these statements. This F inverse of A to infinity, or F inverse of minus infinity to E. Because this one, it's very simple to use. So let's prove this theorem first. First we show that this first implies second, then we show second implies third, third implies four, four implies five, five implies six, then finally we will show that 6 implies 1. So we will prove it in sequence, and this will prove these all these 6 statements, they are actually equivalent. Okay. So let's first prove first implies second. First implies second. Proof. First implies second. Actually, it follows from the definition. So if F is measurable, means inverse image of every open subset of R is measurable. So this should imply, in particular, inverse image of every bounded open interval is measurable, because bounded open intervals, they are open subsets of R. So since inverse image of every open subset of R is measurable, so therefore in particular inverse image of every